Welcome to the Deep Dive. This week, we're continuing our special series featured in the PXRD newsletter on Substack. We're really immersing ourselves in the nuances of overhead and underground electrical construction. It's all about understanding the engineering rationale behind why certain types are used and, the characteristics that define them.
Exactly. We've already covered heavy angle and vertical framing and touched on identifying types out in the field. So today, Thursday, in our series, we're dissecting what might look like the simplest of them all, but it's undeniably the most pervasive and critical component of our distribution systems. Tangent framing.
Right, the quiet backbone, often underestimated, I think, because its elegance really lies in its simplicity. So our mission today is to unpack the sophisticated engineering that underpins tangent construction, its efficiency, its huge economic impact, and why it's really the unsung workhorse doing the heavy lifting out there. Okay, let's dig into this.
Yeah, let's do it. So when we talk about overhead electrical distribution, tangent construction isn't just a configuration. It really is the foundational standard.
Your standard, okay.
Yeah. While other types, dead ends or heavy angles, they might get more engineering attention because they're complex. But tangent structures, they carry the vast majority of the electrical load. They span most of the miles in, pretty much any distribution system. They're literally everywhere.
You called it the unsung workhorse. Why do you think it's often overlooked? And is there one detail about it, maybe an engineering detail, that even folks in the industry might underestimate?
Well, I think because they're everywhere, they just seem normal, mundane, maybe.
Mm-hmm.
But the real genius isn't just the upfront cost saving, though that's huge. It's how that simplicity scales. Think about grid modernization, all the new stuff, smart sensors, fiber optics, that all needs to be integrated. And because tangent poles are so numerous and fundamentally straightforward, they become these ideal low friction points for upgrades.
Right.
It makes large-scale tech rollouts much more efficient than if every single structure needed some kind of bespoke engineering. And the core principle enabling all this is balanced loading.
Ah, balanced loading. Okay, for the engineers listening, that rings a bell. Force, vectors, equilibrium.
Yeah.
Can you elaborate on the practical side of that for tangent structures in, a real-world design context?
Right. So the ideal balance loading, where the net horizontal force is basically zero, that's the goal. That's what we designed for. But the real engineering challenge is managing the tolerances around that ideal.
Yeah, tolerance, okay.
Yeah, conductors pass continuously through these structures, right?
Got it.
And the tension from the wires on one side is supposed to cancel out the tension from the other side, which means the pole primarily just needs to hold up the weight, so the vertical load. Conductors, hardware, maybe transformer, plus, of course, manage wind pushing sideways on the lines, the transverse load. The tricky part for us as engineers is figuring out how much deviation can we actually tolerate.
Deviation
Like how much of an angle in the line, how much difference in span length between the two sides, or what kind of storing condition. How much can we accept before that assumed balance gets thrown off enough that you get a significant net horizontal force? A force that needs extra support, like a guy wire, or maybe even means you shouldn't use tangent construction there at all. That's where the judgment comes in.
That's a really critical distinction, and it leads to something I found fascinating, the idea that tangent poles are normally not guyed. For many of us, we think guy wires for stability. So how can these often stand alone? What's the principle there, and why is it such a design advantage?
It flows directly from that force cancellation we were just talking about.
Okay.
Since those horizontal forces from the conductors mostly cancel each other out, there's usually no net pull sideways that needs a guy wire to counteract it.
Mm-hmm.
And that's not just, convenient. It translates into really profound economic advantages for utilities.
We know simpler usually means cheaper, sure. But for utility engineers managing these huge systems, what's the scale of this benefit? Is it just a little bit cheaper, or are we talking system-level efficiencies because there are just so many of them?
Oh, it's absolutely system level. It's massive. Think about it in, say, 4 key ways.
Yeah.
First, reduced material costs. Pretty obvious, no guy wires, no anchors, no related hardware for most installations. Seems small per pole, maybe?
But times thousands.
Exactly. Times thousands, tens of thousands. The total saving is huge. Second, simplified construction. It's just faster to put up a pole without needing to install and carefully tension guy wires. Fewer special parts, maybe less specialized labor needed. Big impact on crew time, project schedules. Third, minimal right-of-way impact. This one's often underestimated, but it's critical. No guy anchors sticking out sideways means you need less easement width. Fewer arguments with landowners, less environmental disturbance. That saves a ton of hassle, time, and potentially legal costs.
Yeah, I can see that.
And fourth, lower maintenance. Simply put, fewer parts mean fewer things that can break or need checking over the years. Less inspection needed, fewer repairs over the pole's life, which would be decades. So, yeah, these aren't small savings. They compound across the whole network.
Okay, so this inherent stability, this balanced loading is
Yeah.
key. Does that mean there are specific places, maybe geographical or environmental sweet spots, where tangent construction just works perfectly? And conversely, are there spots where it's just asking for trouble, forcing engineers to think differently? What are the ideal conditions?
Yeah, definitely. Tangent construction really thrives when conditions help maintain that balanced loading. This is where site assessment is crucial for engineers. You're primarily looking for straight line routing, minimal angle in the line path, ideally less than, say, 2 or 3 degrees. Any more, and you start getting that net sideways pull.
Okay, keep it straight.
Keep it straight. Then, consistent span lengths on both sides of the pole. That's vital. Even a difference that seems small, maybe 50 feet on a 300-foot average span, can create significant unbalanced tension, especially when it gets really cold and conductors tighten up. We've definitely seen cases where overlooking that led to poles slowly leaning over time. Then you're looking at costly fixes, maybe adding guys later or even replacing the pole.
So consistent spans. What else?
Uniform conductor types in that section. You want the same type of wire throughout to keep the weight and tension characteristics consistent. And finally, it does best in generally moderate environmental conditions, areas that don't regularly get extreme high winds or really heavy ice loading. Those kinds of events can create temporary but very large unbalanced forces that could push an unguided pole past its limits.
It sounds like a lot relies on the pole itself and this balance, but the hardware connecting the wires to the pole, the insulators and clamps, they aren't just passive hangers, are they? Are they actively involved in keeping this balance?
Oh, absolutely not passive. The idea that it's just a simple hanger really undersells the engineering in that suspension hardware.
Okay.
Take suspension insulators, for example. They're the bits that let the conductors hang from the pole but continue straight through to the next span. But that hardware is designed for dynamic response. It has to absorb the conductors bouncing or swinging in the wind. It has to handle the wires sagging more in the summer heat and tightening up in the winter cold daily and seasonal cycles. And critically, it has to maintain electrical insulation, even if it gets dirty or during voltage surges. It's a really precise mix of mechanical strength and dielectric performance.
So beyond just holding the wire up, what specific stresses or, say, performance metrics does that hardware need to handle? Things engineers might really face out there.
It's got several critical jobs. First, vertical loading, obviously. Supporting the plane weight of the wire, sure, but also any ice buildup. Ice can add a huge amount of weight, changing sag and tension dramatically.
Right, ice is heavy.
Very. Then there are swing loads. The hardware needs to manage the conductors swinging in high winds without putting excessive damaging force on the pole or the conductor attachment point. It's designed to allow some controlled movement, not be totally rigid. Also, thermal movement. Like we said, conductors expand and contract with temperature. The suspension system has to allow for this movement day in, day out, season after season, without causing metal fatigue or other stress issues. And always paramount, electrical requirements. It has to provide enough insulation preventing electricity from flowing into the pole structure and maintain safe clearances from everything else, other wires, the pole, the ground. That ensures safety and keeps the system running reliably under all sorts of conditions.
So even if those horizontal forces are mostly balanced, these tangent poles aren't just sitting there passively. They're dealing with quite a few significant loads constantly. Can you break down those different load components that engineers have to factor in, even for these seemingly simple tangent poles?
You got it. While the ideal is balanced horizontal conductor forces, tangent poles always have to manage other loads. Some are constant, some vary wildly. You've got dead loads. That's the permanent weight. The conductors themselves, the insulators, clamps, maybe a transformer bolted on, or switches. Stuff that's always there.
Okay, the static stuff.
Right. Then live loads. These are the variable ones. Wind pushing on the wires and the pole, ice building up, even temporary forces during maintenance work, like a line worker on the pole. We also consider dynamic loads. These are trickier. Forces from things like conductor galloping, where wires can start oscillating wildly in certain wind and ice conditions or just swaying. These can put unexpected stresses on the structure. I actually remember early in my career, a classic case. A line that looked perfectly fine, tangent construction, started galloping like crazy during one specific wind event. Wasn't expected, but it was let's say, a vivid lesson in why you factor in those dynamic forces even on simple lines.
Wow. Yeah, you wouldn't necessarily think of that.
No. And finally, equipment loads. This is specifically the extra weight and also the wind profile added by things like big transformers, capacitor banks, switching gear mounted right on the pole. They add weight, shift the center of gravity, and catch more wind.
Okay, so given all these loads and the need for balance, are there times when those ideal conditions just aren't met? When you have to tweak the standard tangent design? Does it sort of break its own rules sometimes, forcing a modification?
Oh, absolutely. Engineers have to be ready for that.
Yeah.
Certain situations definitely compromise that balanced loading idea and force modifications.
Like what?
Like significant span differences. We touched on this. If one span going into the pole is much longer or shorter than the one leaving it, the tensions won't balance. That net horizontal force might be too much for an unguide pole, so you'd likely need to add a guy wire for stability.
Okay, makes sense.
Or heavy equipment loading. Putting a really large transformer or maybe multiple capacitor banks or heavy switches on a standard tangent pole might just overload it structurally or create an imbalance. You might need a stronger pole class or guying or maybe even a different structure type altogether.
Right.
Also, severe environmental factors. In places known for extremely high winds or very heavy icing or huge temperature swings, you might need to beef up the pole or add guys even for straight tangent sections. The temporary live loads during storms could just overwhelm the standard design's inherent balance.
Planning for the extremes.
Exactly. And one more. Future expansion. If you know that down the road you plan to add another circuit or more equipment to that pole line, it might be smarter and cheaper in the long run to build it stronger. Now, maybe a heavier class pole than current loads strictly require. Planning ahead.
This really hammers home that what looks simple on the surface often hides some pretty sophisticated engineering. The economics are obviously huge, as you've laid out. But does this very simplicity, this pervasiveness, ever create maybe a blind spot for engineers, like maybe leading to assumptions that don't hold up in extreme cases or discouraging innovation for these basic structures?
That's a really insightful point. Looking at the bigger picture, the economic efficiency, why tangent construction is the default, the go-to choice whenever conditions allow it. By keeping structural needs minimal while still being strong enough, it optimizes that cost versus reliability equation that utilities are constantly wrestling with.
Correct.
And that efficiency is magnified by the sheer scale. Like we said, thousands and thousands of these tangent structures for every specialized pole, like a dead end or a heavy angle. So those small savings per pole add up to massive system-wide economic benefits. But the blind spot risk you mentioned, it's definitely real. It's easy to start treating them like interchangeable commodity items, maybe not giving each location the specific thought it needs.
And it's not just about the money, is it? It boils down to basic grid reliability. If these simple-looking poles are everywhere, they have to be incredibly dependable day in, day out.
Exactly right. Tangent construction might be conceptually simpler than, say, designing a big angle structure, but it absolutely demands proper, rigorous engineering analysis. Poles have to be sized correctly for the absolute maximum loads they're expected to see, considering the worst-case mix of wind, ice, conductor tension, and they need adequate safety factors built in. That extra margin covers uncertainties, ensures they last for decades, meet service life goals, and, critically, comply with all the electrical and structural codes. That's non-negotiable. So yeah, tangent construction might seem mundane next to the drama of a dead end holding back massive tension, but it truly is the foundation of distribution reliability. These are the structures carrying the bulk of the energy to homes and businesses. They have to work reliably, day after day, year after year, through sun, rain, wind, and ice. Understanding tangent construction, its strengths, yes, but also its limits, is just fundamental for anyone working in overhead distribution.
So, thinking about that, the next time you're driving down a road, maybe stuck in traffic, and you see those long lines of utility poles just stretching out, how might your understanding of tangent construction, this seemingly simple design, change how you look at those everyday structures? And maybe appreciate the massive kind of unseen engineering effort that keeps everything powered.
It's a powerful reminder, I think. Often the most vital parts of any complex system are the ones doing the heavy lifting quietly, efficiently, almost invisibly. Their brilliance is in that simplicity, but it's a simplicity that still requires precise engineering, even in something so common.
That's all the time we have for today's deep dive. Thank you so much for joining us for this segment in our special series.
And definitely tune in tomorrow, Friday, for our final deep dive in this series. We'll be tackling debt in construction.
If you'd like to leave feedback or have any questions, feel free to reach out to us. You can email me at alex.reed.power.podcast@gmail.com.
And you can reach me at emma.quinn.power.podcast@gmail.com. Thanks for listening.